Welcome students. So today I will discuss about the electrical actuators. Okay, so this is Mechatronics lecture number 17. Okay, so what is electrical actuator? So first I will tell you what is the meaning or what is the definition of a actuator. So it is a mechanical device or a system which has the motion or movement, that is called as actuator. And what is electrical actuator? An actuator receiving electrical energy for the motion or movement is known as electrical actuator. So it consists of your two parts. One is your switching devices or switching circuits, and another one is your drive system. In switching devices we have mechanical switches, solenoids and relays, and in drive systems that is DC motor and AC motor. Okay, let's see one by one. So first see the mechanical switches. Okay, the mechanical switches are the elements which are often used as sensors to give the input to the system. For example, your keyboards. Okay, so mechanical switches are those where in switching action is by the application of force on the switch, and during switching action mechanical elements move with the switch. Clear? So mechanical switches are specified in terms of first one is your number of poles and the number of throws. Number of poles is denoted by capital P and number of throws is denoted by capital T. So poles means capital P are the number of separate circuits that can be completed by the same switching action, and the number of and the throws, that is T, are the number of individual contacts for each pole. Clear? Okay, now let's now let's move to the now look here. Okay, so switches are characterized by the number of poles, number of throws, and whether connections are normally open, that is NO connection, or normally closed, that is NC connection. You can see the figure. It is a no push button, and SPST means single pole single throw button, and second one is your NC push button, numerically normally closed, and SPDT means switches changes the pole between the two different throw position. Okay, and SPST means it is a switch is in a single pole and single throw device that opens or close a single connection. Okay, so this is all about your switches. So let's move to the solenoid. First you look the figure. One is your plunger, figure number A is your plunger type, and figure number B is your non-plunger type. What is the difference that you feel? In a plunger type there is a central movable armature, and is a non-plunger type the movable armature as the top of the spring. Clear na? So and the coil is wounded in the movable armature in figure A, and here in figure number B the coil is wounded in the left part of the iron core. Okay, okay, so and the outside body is a stationary iron core, and the movable and the means centrally part iron is your stationary type. ठीक. Okay, now let's see the discussion. So now look here. A solenoid, it consists of a coil and a movable iron core, and movable iron core is your armature. Okay, and when the current is passed through the coil, it gets excited, and consequently the core moves to increase the flux linkage by closing the air gap between the cores. The movable core is usually spring loaded to allow the core to retract when the current is switched off. Okay, the force generated is approximately proportional to the square of the current and inversely proportional to the square of the width of the air gap. Okay, so solenoids are inexpensive and it can be used to provide electrically operated actuators. So solenoid valves are the examples of such devices being used to control the fluid flow in hydraulic or pneumatic circuits. So they are frequently used in your washing machines, valves, automobiles, that is door latches and starter solenoid, and in factory automation. Clear? So let's move to the relays. Okay, so this is the third type of switches, that is relay. Okay, fine. So see, the relays are electrically operated switches in which changing current in one electrical circuit switches the current on or off position in the another circuit. Okay, and relays are often used in control systems. The output from the controller is a relatively small current, and a much larger current is needed to switch on or off the final connection element. For example, the current required by the electric heater in a temperature control system or a motor. Next point is your a relay performs a function similar to the power transistor switch circuit but has the capability to switch much larger currents. The input circuit of a relay is electrically isolated from the output circuit, unlike the common emitter transistor circuit where there is a common ground between the input and the output. The main disadvantages of the relays is that they have very slower switching times as compared to the transistors. So students, this is all about your mechanical switches, solenoids and relays. So next type of electrical actuator is your driving system, that is today class I will discuss the different types of DC motors. Okay, so let's move to the DC motors. So DC motor means direct current motors. So mostly preferable motors used in mechatronics, that is your DC motors as compared to AC motors. So DC motors are four types. One is permanent magnet DC motors, shunt magnet DC motors, series DC motors, and compounded DC motors. So let's check one by one. First one is your PM DC motors, means permanent magnet DC motor. As you can see here, it is in the figure. Here is the supply voltage V, and here is the positive terminal where the current flows from high terminal to low terminal. Here is the armature, and a magnet is coupled with the armature. And in the side by side you can see the torque speed graph and the current torque graph. This is the linear graph. Why? Because it is permanent magnet DC motor. Permanent magnet means the flux produced in the circuit is constant. That's why the relationship between torque and speed and line current and torque is a linear relationship you are getting. Okay, so let's discuss the PM DC motor. So in these motors, the field excitation is obtained by suitably mounting the permanent magnets, which require no power source and therefore produce no heating. This is the most important point. And the magnets are made of ferrites. It is lighter and smaller than others equivalent DC motors because the field strength of the permanent magnet is high. So permanent magnet motors are easily reversed by switching the direction of the applied voltage, because the current and field change directions only in the rotor. Clear? So next move to second type, that is your DC shunt motors. Okay, DC shunt motors. Okay, so here look here the figure. Here the armature is placed in the middle. So what happens in DC shunt motors? In DC shunt motors, in these motors, the armature and the field winding are connected in parallel. Okay, are connected in parallel and powered by the same supply. Same supply voltage is given to the armature and the field winding. Suppose let by the supply of V there is line current is I, and as it is a parallel connection, so current will divide in the armature circuit and the field connection. Let IA is the shunt, let IA is the armature current is passing through the armature, and ISH is the shunt current passing through the passing through what? Field windings. Clear? So now here you can see the torque versus speed and line current versus speed graph. Okay, so these motors exhibit nearly the constant speed. You can see in the graph nearly the constant speed over a wide range of or long range of loading. Okay, so they have starting torque about 1.5 times the rated operating torque. Okay, and they have lowest starting torque of any of the DC motors. They can be economically converted to allow the adjustable speed by placing a potentiometer in series connection with the field windings. Clear? So this is your DC shunt motors. So next one is your DC series motors. Okay, this is your DC series motors. Okay, look the figure first. So here as the name suggests, it is a DC series motor, means the armature and field winding are connected in series. In series means the current will same for armature and for field winding. So in this type of motor, the armature and field windings are connected in series, so the armature and field currents are equal. Now look the graph between torque versus speed and current versus speed. You have very high torque at very low speed. Okay, so these motors exhibit very high starting torque, highly variable speed depending on load, and very high speed when the load is small. Okay, so the torque speed curve behaves like a hyperbolic shape that implies an inverse relationship between the torque and the speed, and nearly constant power will be developed over a wide range of speed. Clear? So this is third type of DC series motor, third number DC series motor. Let's move to the final. It is DC compound motor. Okay, DC compound motor. Okay, so look the diagram carefully. Okay, fine, look here. So and there are two fields, one is series field, one is shunt field. Okay, and look the torque versus speed and line current versus torque graph. The compound motor has a shunt field winding in addition with the series winding, so that the number of magnetic lines of force produced by each of its poles is the resultant of the flux produced by the shunt coil and that due to the series coil. Okay, the flux so produced, it depends not only on the current and the number of turns of each coil, but also on the winding direction of the shunt coil in addition to that of the series coil. When the two flux combine each other or assist each other, the machine is a cumulative compound motor, and when they oppose each other, it will be a differential compounded motor, differential compound motor. So up to this we have covered the mechanical switches, solenoids, relays, and different types of DC motors. Thank you.